Welcome back to BAS 120. My name's Mr. Rankin. We're going through Chapter 1, and this is the second part. We're going to start talking about data, the use of data for business analytics. So some of the key topics are going to be the different types of data. Then we're going to talk about decision models, how to put a mathematical model together to help us make decisions. The steps in problem solving. So that'll take us through the remainder of the Chapter 1 in the book. We've added a couple of topics onto this around data validation and data ethics. Two important topics that we're not going to go into a lot of detail into, but I thought it was important for you at least to have some visibility to those topics. So let's get a couple of key terms out of the way. First of all, data or data set is only a collection of different data, a collection of different information. When we put it into what's called a database, then we have a collection of related data or data that's consistent and then or related to each other. Then we put it into what are called fields or attributes, which you can see here, such as customer name, customer number, invoice number. These are called fields or attributes. And then in the database we have what are called individual entries or records, such as the name Johnson, such as the actual measure of 100. So a database is a way to provide us a method of organizing information with fields and attributes in entries or records. Now, a metric, another key term, is a metric. So a metric is a unit of measure that provides a way to objectively quantify performance. So for example, the score of a baseball game, a business's earnings or revenues, the number of defects per million is a quality measure. Now these are all metrics, the score, the earnings, the quality performance. Measurements are the actual act of obtaining the data associated with the metrics. So the metric might be the score of the game. The actual measurement is 5-4 is the score. Now, once we get by some terms, let's understand the different types of data. Now, unfortunately, different books and different disciplines are going to name these things a little bit differently. But let's start off at the top. We have data. Now, a lot of mathematic folks, if you take a mathematics statistics course, they're going to probably split it between two categories. They're going to take qualitative data, sometimes called categorical, and they're going to take quantitative data. Quantitative data is basically numeric. Qualitative is basically non-numeric. Our book splits it into four categories here highlighted in green. But the qualitative data is split between categorical and ordinal data. And then the qualitative is split between interval and ratio data. And we'll explain these four on the next slide. And then further down, these quantitative measures can be split between whether they're discrete numbers between them, because remember, these are all our numeric data. These are all our qualitative or categorical data. Our numeric data can be split between discrete and continuous. Continuous meaning all the numbers are filled in. Discrete meaning like 1, 2, 3 steady increments. Now, back to the way our book defines it. 4 categories: categorical, ordinal, interval, and ratio. Now, categorical data, and the reason for these things is you always measure the data by the highest level that it satisfies. So if it satisfies the requirements to be ratio, it's ratio. But in order to be ratio, you also have to be mutually exclusive. You have to have covered all these other areas too. So categorical data is things that are mutually exclusive, but not ordered, and you can only put them into categories. So examples might be different eye colors or geographic regions or employee classifications or name etc. Categorical data, you put them into categories, and that's about the extent you can do. And as we get into more statistics, we'll see this becomes very important because you couldn't, you'd not, if somebody said, what's the average eye color in America, it would be relatively meaningless. The next type of data is ordinal. Here we can order or rank things, but the order matters, but the difference between each measurement doesn't. You don't know. So it might be like college football ratings. You can rate them from 1 to 20, but it might be team number 1 is way, way better than team number 2, and team number 2 relative to team number 3 are very close. So there's no difference in each range on ordinal data. Interval data has a constant difference from number to number to number, like time has a constant 1 o'clock to 2 o'clock as an hour, as is 2 o'clock to 3 o'clock. But there's no zero, there's no start time. Temperature works much the same way. Time and temperature are great examples of interval data. So even though I can say 2 o'clock is an hour later than 1 o'clock and 3 o'clock is an hour later than 2 o'clock, I can't say 3 o'clock is 20% later than 1 o'clock because I have no natural zero, so I can't do any ratio analysis, which is the final type of data. That's where I have continuous data, but I have no zeros. So for example, sales volume might be the case. I can say, $100 to 150 to 200 is equal increments, but because I have a natural zero, in most cases, in this case it's 0, I can say 150 is a certain percentage more than 100, 50% more. So categorical, ordinal, interval, and ratio. So just to give you an example, Johnson would be categorical data. Customer number, I can order it. It would be ordinal, but it doesn't necessarily mean I don't know that there's 101, 102, 103. I think there's a typo in the book. It might have said this was categorical. Invoice number, the same thing. I think there might be a typo. This is ordinal data. The dollar amount is ratio data because I can do, this order was 20% more than that order. Product, all I know is categorical. Interval would be your dates and your temperatures. Date is interval. I can tell you the interval from one step to the next is always the same, but I have no natural zero, so I can't say January 15th is X% more than a different date. So there is a summary and examples of categorical, ordinal, ratio, and interval data. Finally, as we mentioned, we can have discrete metrics. That's what they can be counted, like on-time delivery, pass inspection, order completeness, or they can be continuous based on a continuous scale, like dollars, times, and weight. So on your numeric data, it can be discrete or it can be continuous. So now we've talked about the types of data. Let's talk briefly about different decision models. So all a decision model is a logical or mathematical representation of a model, of a problem, or a business situation. So it could take three forms. You could say, how long is it going to take me to mow the grass, for example? Let's have a model for how long it's going to take me to mow the grass. Well, I could do a verbal description. I could say, to mow the grass, it takes a long time when the grass is really long and it's really, really wet. But it doesn't take so long when the grass is relatively short and it's dry. That would be a verbal description. Oh, okay. Now I know when it's subjectively when it takes longer, when it takes shorter. I could do a graph. I could graphically show it to you. I could say, here are the plots. Based on my x-axis, I might have length of grass, and the y-axis, how long it takes to mow the lawn, and I could graphic. And you'd probably notice, oh, I can graphically see the longer the grass is, the longer it's going to take to mow the lawn. The last thing I could come up with is actually a mathematical model. I could say, to mow the grass is y might be how long it takes me to mow the grass. grass, and that's equal to 2 times the length, my x, the length of the grass, plus perhaps some fixed amount like 5 minutes that it's always going to take to mow the lawn because I have to set up and etc. In this course, we will be working mostly with mathematical models or functions. And all a decision model is you take your inputs, and we'll show you the different kinds of inputs. You put them into the model, which is normally a mathematical function, and that mathematical function, based on the inputs, will give you an output or a solution. So that's all decision models are. Now, let's talk a little bit about the different inputs. We could have a constant for input, in other words, a constant in a model, a number that doesn't change, like machine capacity, or in this example, we're going to do an example of a family budget. So for my family budget for next year, I'm going to make the assumption or the data input that the size of my family is constant. I mean, I'm older, I've got 4, it's a family of 4. It's very unlikely that that's going to change. So that's a constant in the model. It's called data constants. Then I could have uncontrollable variables. In this example of a family budget, an uncontrollable item might be the size of my bonus at the end of the year. I don't know how the company's going to do. I don't know what percent bonus they're going to give. That's a surprise every year. It's an uncontrolled variable. I have very little control over what my bonus is going to be. Finally, you have what's called decision variables. So oftentimes in a business, that would be my staffing levels, etc. In this example of a family budget, I can have a decision variable be, well, do I buy that new car this year or do I wait till next year to buy the new car? I can look at my model and I can change my decisions on my decision variables. So you have constants, things that really are not going to change. You have uncontrollable variables, things that are probably going to change, but I have very little control over. And then I have decision variables, things I can make decisions on to make changes. So those are the 3 different types of input variables that you have into your decision model. So often in developing these decision models, we do what's called an influence diagram. We actually diagram out what the different things are that impact, say, total costs in a business. So total costs are the addition of fixed costs plus variable costs. And variable costs are simply made up of my unit variable cost times my quantity produced. So let's say I'm making a hot dog stand and each hot dog costs me $1 and I make 100 of them. That's 1 times 100 is $100 it's going to cost me. And then my fixed cost might be the rent of the stand, $25. I pay $25 irregardless how many I produce or sell. So it would be 1 times 100 would give me 100 plus my 25. My total cost would be 125. Represented as a model, TC, total cost, is equal to fixed cost plus my unit variable cost times my quantity produced. And you can just, whatever the assumptions are for fixed cost, unit variable cost, and quantity produced, you can plug them in and determine what your total costs are going to be. So that's a model using an influence diagram. Now let's talk about uncertainty and risk and the difference between the two. So uncertainty is any time we don't have we have imperfect knowledge of what's going to happen, which is almost always, particularly when we're modeling. If we knew what was going to happen, we wouldn't have to model it, right? So let's say boarding time on an airplane. If the plane's going to be on time, that's certainly unknown. It's uncertain. We could say we feel pretty comfortable because 70% of the time it's been on time, but we really don't know. It's uncertainty in our model. Risk comes into play when we talk about the consequences of what happens if that uncertainty actually happens. Well, if I'm not scheduled to be on the plane, then the plane being late presents no risk to me. It's only a risk if I have a ticket to be on the plane. So uncertainties out there, it's imperfect knowledge of what will happen. The risk is just the consequences. Well, if I'm not on the plane, there are no consequences. Next, let's talk a little bit about optimization. Remember, this is where this is prescriptive analytics. This is where we let the model explain to us how the best solution would be. So optimization is actually the process. What you have is you have what's called an optimization function. So most of us have GPSs in our cars or have used GPSs. GPS is a great example of an optimization equation. What you do is you give it a function, an objective function, oftentimes is get me there the fastest way or minimize the number of miles I drive, right? We might, lots of GPSs allow us to put in constraints. Ooh, I want to avoid I-95 because I don't like driving on I-95 because of the traffic. And what the GPS comes back to us is what's called an optimal solution. It models and it gives us the route to go. So that's optimization, optimization function, constraints, and optimization solution. Now let's talk a little bit about knowns versus unknowns, or more dramatically, deterministic is the known, stochastic is the unknowns. Now, a model can either be deterministic or stochastic. But let's think about this for a minute. Why would we model something where everything's already known? So very, very rarely do you do a lot of models where you have them known. But anyways, an example of a deterministic model would be, let's say, in the short term, the rotation pattern of the planets around the Earth. And let's say for the short term, the next day. So I think it's pretty safe to say in our deterministic model that the sun's going to come up tomorrow. Right? We've modeled it. It's happened for 5,000 years. It's always come up. I think we're pretty safe in assuming that the model, the knowns are all knowns. Not a lot's going to change on the planetary rotation in the next day. A stochastic model might be the weather forecast. Lots of uncertainty, lots of unknowns with the weather, lots is changing, very dynamic, and that's usually what you're going to model. You're not going to model things where there aren't any unknowns. Because if there aren't unknowns, I mean, who would go out and model whether the sun's going to come up tomorrow? Lots of models on what the weather's going to be for tomorrow. But that's the difference between deterministic and stochastic models. Let's talk a little bit about the steps of problem solving. Book outlines 7 steps. First, you've got to recognize the problem, which is normally some sort of gap between actual results and what we expect. You know, we step on the scale and say, oh my God, I've gained 5 pounds. I'm 5 pounds more. I've got a problem. And then you normally define the problem. And when you define the problem, you want to involve as many of the stakeholders in the solution as you can. You may call a meeting and get different people from different functions together and say, how do we solve this? How do you get a stake in this? Then you structure the problem and you put what are the goals, what are the constraints, what are we trying to achieve, what does success look like, etc. What are some of the constraints? Might be budgetary constraints. Then this is the key area for analytics. Then we come in and we analyze the problem. We take a look at the data, either historically, or we can run some optimization equations. How do we analyze this problem with data-driven decisions to say, what does the data tell us about this problem? Where does the data tell us? We might do some Pareto analysis to see where the most influential portion, the biggest impact, etc. Lots of analysis that can be done. 5, we interpret the results and help make the decisions. Normally, most people don't run just on data. They're going to add in some human intelligence into it. And then we implement the solution and look for buy-in from all our stakeholders, make sure we have the adequate resources, and continue to monitor the situation to continuously improve. So those are the normal steps in problem solving. So we've gone through the remainder of Chapter 1. We've talked about types of data. We've talked about decision models. We've talked about the steps in problem solving. Now I want to walk through very briefly 2 steps that are also important on data validation and data ethics. So sometimes it's called validation, sometimes it's called data cleansing, again, lots of different terms. But a couple things we want to look for in our data before we can even start analyzing it. First, we want to look at the form of the data. Are all the mandatory fields entered? Lots of programs, such as Excel and others, if there's missing data and missing fields, it won't perform the proper analysis. So we've got to make sure, from a form perspective, any missing data we've accounted for or eliminated, in it where we have mandatory fields, there are entries. Next thing we need to check for is check our fields. We need to make sure that categorical fields have categorical data. We've got to make sure our numeric data have fields or attributes have numeric numbers in there. And there's software packages that can help you check for this. Last thing we need to look for is some sort of range or graphing of the data. This will help us see if there's any outliers or any errors. We may put in the average salary for different people, and we might have added a zero, 2 zeros on entry, and somebody's making $50 million, right? And we need to account for that. So we need to look at the range by graphing or doing some min-max. But we need to check some of these areas for data cleansing or validation before we even start doing the analysis. We got to make sure our data is clean. And there's lots of tools that are available and more coming on the market every day that help us with that analysis. Finally, I just want to touch on data ethics. A couple areas we got to make sure as we analyze data. Certainly, we want to make sure that we're not falsification of anything. We want to make sure that we don't have biased results. We want to try to make sure that we go in with an open mind and we don't have an answer that we're looking for data to justify. We know the answer, and regardless what the data says, we're going to falsify the data to fit our preconceived conceptions. Secondly, we got to make sure that we don't have poor data gathering. That's also going to bias our results, and we'll talk about that in later chapters on sampling techniques and stuff like that. Third, we got to make sure that our data storage is in good shape and not suspect to lots of folks getting their hands on it and compromising the information. Finally, we got to be very conscious of the confidentiality of the information. Make sure it's only in the right hands of the right people, because data is a very powerful tool and we have to respect it. So that's data validation and data ethics and the entire chapter 1. Any questions, let me know.